All right, Sam. Just making sure this is okay with you that we record this and post this on YouTube.
Yes, so we are happy to participate in this.
Very good. And we have Sifan Du from the University of Texas at Austin presenting work that she is doing with James Howison. Fan, if you want to introduce yourself a little bit more, and then we can get started with the presentation.
Sounds good, thanks. So, hi, I'm Fan. I am a current doctoral student, and I work with James Howison at the School of Information at the University of Texas at Austin. So I have been studying scientific software work. So we are very happy to be able to give this presentation on kind of our understanding of the scientific software ecosystem in the College View Workshop 2020. And for the theme of this workshop, developer productivity, we would like to propose an ecosystem view to examine developer productivity and how would the developer work be like from the perspective of a scientific software ecosystem. So first, let me talk about, to define software ecosystem first. So software ecosystem is a set of interconnected software projects and the actors and the stakeholders engaged in software work. And particularly in the context of science, software ecosystem are a set of scientific software projects. They grow amid scientific institutions, including universities, research centers, laboratories, funding agencies, science policy making organizations, professional societies, and so forth. So as I listed so many organizational entities that has relevance to the science context, you can see that scientific software work has to deal with quite complex organizational environment, and it is not uncommon for scientific software projects to react to the requirements or expectations or even visions from those organizational entities in science. And scientific software work, in comparison with the software work perhaps in industry or purely community-based peer production space, perhaps, scientific software work is particularly complex because it has to deal with the progress of science. So scientific software work and science go hand in hand. Scientific software work has to react to the emergence of new methodological treatments, research techniques, data sets, etc. So that makes scientific software work more challenging. And what's more, scientific software work has to deal with its technology complexity. So externally, scientific software needs to react to the upgrades of hardware and perhaps scientific instruments. But within the scientific software ecosystem, we speak of the technology complexity of scientific software in terms of its dependency structure and complementarity. And we refer to these two kind of characteristics of scientific software technology complexity as its use context. So to illustrate it more, let's first think about how do researcher developers use scientific software components. So here this diagram illustrates what we call a software assemblage like. So think about a researcher developer. She wants to have a solution to a scientific program, perhaps output some data or code to provide a solution to reach some scientific findings. And she pick and combine different scientific components. And essentially these components, these individual components are themselves software stakes with their vertical dependencies, as you can see on this diagram. And they combine these components into a workflow, like perhaps start from data collection to pre-processing data analysis procedures and then followed with some post-processing and data representation. So that's what we call a software assemblage, and that's quite usually how research developers use scientific software components. And usually researchers or scientists work with the software assemblages intensively while, say, they are preparing a scientific publication. And once the publication is done, perhaps the researcher will leave the assemblage alone for some time. However, in the long term, the researcher developer will periodically revisit her software assemblage for perhaps pick a component for reuse or for extend this assemblage for getting further capabilities from it. And the assemblage itself is not static. It's constantly shifting in terms of all these components that consist of this assemblage. They are in constant updating, releasing, and perhaps bug fixing. So the assemblages change over time, and that leads to the issue of dependency hall, or we call high ongoing maintenance cost of scientific software assemblages. So essentially, because code are changing all the time, and it's common, when I am a graduate student and when I work with my advisors old code, I was crazy about the dependency hall, that the time that I spend to solve that is far longer than I get the results from, and aware the code in its good status. And that really demotivates researcher developers to work with software and potentially undermine their productivity. And what's worse, one scientific component changed, and all the other software assemblages that contain that component will be faced with a series of changes. So this problem will cascading within the scientific software system, reaching a certain order of magnitude. And what's more, because developers in the scientific software space don't usually have usage data to know how researchers use and combine their software components. So one outcome from that is the production and use of software components are drifting away from each other. And in the long term, this will lead to high technical debt that science needs to deal with, though they currently don't really have a very effective mechanism to deal with, perhaps. And when that debt comes to a certain scale, the issue will become intractable. So the image of ecosystem disorder that I just described is driven by two factors. Essentially, first is the number of users of one individual software components. It's all the different software assemblages that reuse that software components. The more people use it, the more possible that changes occurs within those software assemblages, and then the issue will be transmitted across all these software assemblages that use that component, and the issue will scale. The second factor is the diversity of use. So one software component is often used in different scenarios, being combined with the other different software components with different dependency structures. And that diversity of use leads to, so change happens in one assemblage. If you manage to solve that, because say a software component, there is a version update, and you update your code because there is a function which is soft deprecated. But in other software assemblages, this issue hasn't been solved, so that your local solution don't really scale up or cannot be reused across different use scenarios. So we have this diagram, theoretically speaking, driven by the number of users and the diversity of use contexts. scientific software ecosystem is facing increasing ecosystem complexity, and each different software components may lies at a different position on this diagram, and plus the frequency and the pace of the component change are different. So each change of one single component are changing at a different pace, and they scale up. So as you can imagine, this issue just become increasingly intractable. So to counteract the ecosystem disorder, we identify 3 types of work that is needed at the ecosystem level. The first is the sensing work. That means for the producer of the component or the user of one's software component, how they could understand the changes in its assemblage, in the whole assemblage. Any single component in that assemblage, its change could affect the kind of health status of the assemblage itself. So we call this sensing, is to be aware of the situation. There is a need for react to that one single component change for your whole software assemblage. And the second thing is adjustment work. That means you reacted to that perceived change and you did some adaptation work locally. And the third thing is synchronization. That is, if you locally solved that, that issue, but you don't share your solution with others, then the users of your software assemblage will need to assume the subsequent changes due to the initial one single component change in your software assemblage. So we call this synchronization work. Essentially, it is you made change in your local software assemblage, and then you need to coordinate that change with other interconnected components. So all the involved components can make change at a coordinated pace. So that will mitigate the issue raised by the difference in the frequency and the pace of component change. So here we say, from an ecosystem view for scientific software, the challenge would be how to motivate, organize, and implement coordination of the continuous development at the ecosystem level. So essentially, as for one single component change, how we can organize the corresponding change at all the assemblages, all the use contexts in reaction to this single component change. And we really want to raise this question to all the practitioners of scientific software, and I want to know what's your local solution and how do you deal with this issue at the moment, and maybe we will get some really good inspiration from your answers. So thanks, that is all my presentation today.
Thank you very much, Fan. Very nicely stated. Can you go back a few slides to the diagram that you had?
Sure.
Yeah, that one. That's a very interesting chart. I really like that. So if I understand that correctly, what you're saying is that the scientific software ecosystem lives within the white region. Is that right?
Right. Thanks for your question. Yes, because you can see at the upper left, that is when the number of users are high, but it's relatively unlikely that they are all, use the same kind of software assemblage. So that means mass market of identical users, which is less likely to happen. And the bottom right, that is when the use contexts are very diverse, but each use context, essentially, that means each software assemblage only have one user. That is also a less likely scenario. So we kind of theoretically, we think all the software, scientific software should be, crowded in the wide almond area of this diagram.
Yeah. this chart does a really nice job of conveying the complexity of our situation. So
Right.
yeah, thank you. It's very nicely done. Well, thank you so much for your presentation. It's been a pleasure to hear what you have to say and have it emphasized. And just to remind the viewers, the Collegeville workshop, that your white paper is also available, which contains some more detail associated with this topic. And we look forward to your participation in the panel next week. Thank you very much.
Thank you very much.